is. Yeah. Okay. So the conclusion of the discussion is we will meet tomorrow at 2:30 or shortly thereafter, as soon as Guillermo can get there. But yeah, let's say 2:30 tomorrow, Tuesday, and I will let Kevin know. And yeah, I'll send around an email to everyone, just so you've got a record. Okay, so what I've been trying to do is clean up what I've got in the notes about QED. There are several little topics, some things we should talk about, but might not go into in great detail. Renormalization is one thing. I've developed an example to see that we do have a divergence there. I think we've already seen with the scalar field how to absorb that into, well, in that case, it was the mass we changed. But anyway, I'll talk some about renormalization. Then resonances and virtual particles are what happens on the internal lines of the Feynman diagrams. Okay, you say you annihilate an electron and a positron, and they go into this fairly energetic photon, depending. But that photon it's not on shell, right? K squared is not zero for that. You know, it could be sort of anything, and in fact, it's an average of everything. If there's a particle state with a mass corresponding to that energy, you can produce a resonance. So you'll actually see evidence for the formation of that particle. And this is the way a lot of particles are discovered. So we'll talk about resonances tomorrow. And virtual particles are the ones that can't be counted as resonances. So if there's not enough energy to produce a given particle state, we think of it as a virtual particle. These are just names for pieces of something that's already pieces of, you know, some large scattering thing. We don't know what the exact solution is. So they're just convenient names, really. But we do see these resonances at energies corresponding to predicted particles. And so this is giving us real data on particle production. Let's see. So, you know, I want to get through that. The other thing, I've asked you to do the Compton scattering with masses. I've suggested Molar scattering. Molar scattering is a nice, easy one. I think there's only one diagram for that. I forget what it is. Let me remind myself what Molar scattering is. Yeah, I don't know. Let's see. Yeah, Molar scattering. Whoops. Yeah, so why is there? Oh, okay, yeah. Electron scattering. Good. Now, that one's kind of fun because I've lost you all. There you are. That one's kind of fun. Electron scattering. You should see the Rutherford scattering formula in there, right? The 1 over sine to the 4th contribution, but there are all these other terms as well. And the electrons, they can't annihilate. They basically have to just exchange a photon. That's pretty much all that happens at tree level. Where tree level is what we're doing, where you just have basically one exchange going on. You know, try that one. Have you done the Compton? Were you able to get that to work?
Going through it?
With the masses. Did you get through it, Guillermo?
I'm not finished. I'm towards the end.
Yeah, okay, good. Yeah.
I was curious what the cross term was. I feel pretty good about my T and S channel. I'm not so sure about the cross term.
Yeah,
About
that's
that.
tricky. But, let me see, where have I got it? Yeah, I've posted the Compton without the masses. That's online, and you can check your exams there. Let me see, the interference terms. Yeah, I had to work these. They vanish. They vanish in the massless case. But let me have a look. Where did I put that? I haven't included it in the book yet. But okay, let's see. Compton. There we go. So we've got, yeah, the two different diagrams, and let me just look at what happens here. The interference terms. This may be an older version. This, yeah, this is an older. Why do I have this older version here? Yeah, my let's see. 10th. All right. Okay. This is looking right. So for the interference term, let's see. I'm getting T over S plus S over T with a prefactor, sort of the usual prefactor. Are you seeing something like that? There's Alex.
Yeah, so that's what I got for the massless term. I'm more thinking of the mass. Because I am.
Yeah, for the,
all
right. Yeah, I'll
was like the overall one, right? Let's see.
Yeah, I can.
The one I'm getting is like, it's like a mass term over U plus a mass term over S plus a mass term over S times U, or T, I guess, whatever your convention is. It's T and S.
Yeah, it certainly should be proportional to the mass squared, right?
Yeah.
Because we know when we set that to 0, it goes away.
Yeah, or maybe mass to the 4th. I'm getting a mass squared term and a mass.
And a mass to the 4th. Yeah, that sounds right.
Okay.
Yeah,
Maybe I'll just run through it again.
Let's see.
I probably just need to go through the traces one more time and make sure.
That's often the best. I think I'm having trouble finding this because the cloud hasn't updated. It's on my other machine. But you know, I'll post some guidelines. Okay, I can feature the answers so you can check your results along the way.
On my first time through the interference, I'm doing the interference on the massive channel. One more time, and the mistake I made the first time through, it's like immediate, because I got so slap happy with contracting across P plus M that I just replaced all the propagators, the P plus M's, with P minus 2M's, but then had all the gammas in place. So I just decided to change the equation because I'd been doing it for 6 hours and just decided I needed to contract across minus 2M's, and it's just like, okay, that's why it's wrong. Yeah,
yeah, okay. Yeah, these things take some care. So keep trying. I'll update the website on Canvas with the with further guideposts as to what you should get. So Alex, we decided to push this class till tomorrow. Can you make it tomorrow, 2:30?
Is that what we decided? 2:30? Sure.
Yeah, Kevin can make it then. He's traveling today because of the holiday, I guess, but he can make it tomorrow. So let's plan on 2:30 tomorrow. I'll post that on the Canvas site. Let's see. I know I have everybody's emails. So the Canvas notifications don't seem to be as reliable as they should be. So I will send you any updates, any messages via email. So keep an eye on your email. Yeah, I know I can text you as well if you send me what do I need, a phone number or something for text, but it's easy to send you all an email. In the meantime, I'll post more guideposts on the Compton. I have to get on my other machine to figure out what that's supposed to be. Oh, good. Yeah, there we go. Shrugs. Yeah.
Anyone else wants it? Just put it
Yeah,
out there if you want to
yeah.
phone
You
number.
can
There you go.
send me phone numbers if you want. What do you folks prefer, text or email?
Like
Yeah.
email. Email's good.
You like email? Okay. Yeah, I'm used to email because I've been using it longer than most of you have been alive. So, you know, I don't know. I started using email back, I don't know, when was it? The late 80s, maybe early 90s, somewhere around there. Back when the archive was an email distribution, if you can imagine that. A friend of mine from grad school was doing her postdoc at Princeton, and one of the things she did was to compile this list of researchers and gather all these preprints and distribute them. And you know, that was the beginning of the field theory archive. But anyway, it's different now.
I mean, I'd like Canvas, but it just seems like the notifications are troublesome sometimes. I don't know if I'm just being silly with the settings, or it seems like I get them like once a week sometimes. But
no, the only reason I'm using Canvas at all is, you know, because it sets up the recordings. It, you know, pre-programs all the recordings and the Zoom meetings. So, you know, I'll keep doing that, and I'll keep posting things there that you can access. But when I make a change on Canvas, I'll send you all an email too, so you know that way that I've made a change. You don't have to keep checking back. That's easy enough to do.
also, I think I noticed discussion. I don't know if we ever would need a discussion channel, but it might be nice to have it open just in case. Because I was even just looking, yeah, just on the Canvas page.
Okay, you like
that?
Yeah. Huh. Yeah. Let me look at. Let's see. Yeah. All right. Discussions. Oh, yeah. There it is. Yeah, I've got that disabled, but I can enable discussions, I think. Let's see. How do I do that? Probably in settings. Yeah, let me set that up. I think. Let's see. Navigation. Yeah, that's it. And yeah, I've.
Make sure also to change your discussion notification settings. Otherwise, you'll just never know if someone posts anything.
So I'm sorry. What is it I should do? Okay.
I think for the others, just to make sure that they allow discussion notifications to go through either weekly or daily.
Okay. So it looks like I've enabled discussions. I don't know how they work. I never used Canvas before this last year, so I'm really not familiar with all its comings and goings. But if I need to change any sort of setting, just let me know. It looks to me like I've successfully enabled it on our Canvas site. So yeah, so I guess we'll start again tomorrow. If there are any burning questions, I suppose we can talk about it now. But other than that, let's just hold off till tomorrow. Yeah, I can give you like a little sketch of where we're headed. Yeah, a little bit about renormalization resonances. I want to work through that. The one thing that you haven't done that's an important part of QED is calculate the differential cross section for a scattering. And carrying that out can be actually hard because you have to actually do the momentum integrals. And you can, if you've got two particles in the final state, it works out pretty simply. And I've developed the notes on that. I'll post that soon. Yeah, I'll try to post that before tomorrow, in fact. It helps that you've got that conservation of for momentum delta function, because that lets you do half the integrals right away and leaves you with one extra integral. So you can reduce it to 2 degrees of freedom, and those are going to be your scattering angles. So it's not too bad, but you do have to fuss quite a bit with the delta function. So I'll show you some of how that goes. And then, well, after the work of doing those integrals for a general 2-on-2 scattering, we'll have a fairly simple formula for writing the cross section once you've got the matrix elements worked out. So we'll do that. And as I said, finish the massive Compton, do the Molar scattering, electron on electron. I've done Baba scattering in the notes. I'm working a little more on that. These things take a while, and even longer if you want to get them right. Oh, I know, something I need to alert you to. I've changed the normalization. I changed the Feynman rule for the external line insertions for the fermions. I've chosen a different normalization for our basis spinners than what's typically used. And what's typically used is designed to make, to simplify the squaring of the matrix element. So what I did is, you'll recall, I think I gave this as a problem, an exercise to start with 4 orthonormal vectors, 1, 0, 0, 0, 0, 1, 0, 0, and so on, and boost them. And you get the correct form for 4 orthonormal basis spinners, the U's and the V's. Those are normalized to 1, and that makes a lot of sense. The problem is that when you let me think, when you look at the dimensionality of the external lines, okay, those U's and V's survive, and I've showed that, but I didn't work out the normalization you need on those external lines. And basically what you get is a root 2m with each U or V. If you then include that, the normalization that you get from our UU bar is 1/2m times a p slash plus m. And that 1/2m gives you a 1/4m to the 4th or squared, depending on what kind of scattering you're doing. That 2m, or those powers of 2m, cancel with the correct normalization on the external lines. So I've in what I've written for the Feynman rules, I've now put in that correct normalization on the external line, which means that each time you put in a U or a V, you also put in a square root of 2m. All right, and then you'll find after a few steps that all those 2m's cancel. What is usually done with the Feynman rules is you normalize the U's and V's with a factor of 2m to begin with, so that UU bar is just p slash plus m, not p slash plus m over 2m, the way I wrote it. So it's not a normalized projection anymore. It's got this extra 2m. So if you just do everything we've been doing, but you replace UU bar with p slash plus m without the 1/2m factor, you'll get the right normalization there. that's the simple way to do it. But tracing it back to what really needs to be on those external lines or to your normalization of the basis spinners is where that comes from. So be alert to that change. Yeah, I was my cross sections were all coming off by some power of 2m. It took me a while to sort through and figure out where that was. So I changed that in the Feynman rules. You can stick it in and watch it cancel after a few steps if you like. So that said, any other questions before tomorrow?
So yeah, I have a question about that, I guess. So
Yeah.
does that mean that our spinner space then is like a proper momentum space?
Well, the spinner space is, yeah, it's a, yeah, well, proper momentum space. Spinners, Dirac spinners have units. Usually the guideline I follow is that the action should be dimensionless, where h bar and c are both 1. You can express all fundamental physical quantities with units as powers of length. And if you look at the Dirac equation, you've got a d4x psi bar m psi as one of the terms. Now m with an h bar and c in the right places gives you an inverse length. Masses, energies, momenta are all inverse length. So you've got the m is 1 over length. The d4x is length to the 4th. So the field has to make up length cubed. You've got a psi bar and a psi. So psi has units of length to the 3/2. Or sorry, 1 over length to the 3/2. So yeah, it's a momentum to the 3/2 power. The dimensions of psi. When you do the Fourier transform, of course, that's gonna flip. Yeah, I've spent most of the morning tracking through, checking that, you know, the green function, the propagator have the right units, and they do. We're correct on that. It turns out that the Fourier transform, the green function, the propagator, has units of length. You know, it's 1 over p slash. Momentum has units of inverse length. So the propagator, which it's weird, it's the Fourier transform of the green function. The green function has units of like inverse length cubed. I think it is. It's something like that. You can easily check from the equation, but it's probably worth tracking through all those dimensions and figuring out what's going on. So you know, we've got it right at this point, including normalizing those basis spinners to 1, but then normalizing the external lines with an additional √2m. Okay, that's yeah.
Yeah, sorry. So my question basically was just kind of like, if we have a spinner over a space-time, then we kind of have a x and a p space. So my question is kind of like, does the spinner space on the symplectic manifold act as kind of the momentum sector? That was kind of
no,
like,
it's more complicated than that. Probably the object you should be looking at is a superspace. All right, you know, spinners are not momenta. Spinners are anti-commuting fields. So if you're in a superspace, you have both commuting and anti-commuting objects, and so they're natural fields on that. Then you do have super translations, but to really see all that, you need to introduce anti-commuting coordinates, theta A, theta bar A dot, and then derivatives with respect to those anti-commuting coordinates are your translations in the superspace. So they're dual. If you want to understand supersymmetry, I recommend Wess and Bagger as an excellent text on that. You know, working through that. Yeah, you're looking at that, right, Eli? Wess and Bagger. Yeah. Yeah. Send me questions, by the way. Yeah, I need to refresh myself on that stuff. Okay, so there we are. Half an hour into it today. So we'll pick up exactly here, 2:30 tomorrow. I'll send a confirmation email, but look forward to seeing you all then, and we'll compute some more stuff. Following, you working through some more cross sections and me touching on these various topics, we'll start talking about non-abelian gauge theory. So we'll be looking at the weak interaction and things like that. So lots of fun stuff coming up. Okay. So
Good.
Thank you. Thanks, Professor.
see you
Talk to
tomorrow. All right. Bye.
Bye-bye.
Forget how to stop this thing.